All right, let's finish up the notes from today. I believe this is where we left off. So this first line is actually a really important point. A polynomial function of degree n with real coefficients has at most n real zeros. So that's saying if we've got a second degree polynomial, it'll have at most 2 real zeros. A third degree polynomial will have at most 3 real zeros. Okay? It says at most because we could have fewer than that. Right? It's possible that if we have a quadratic, that it has 1 or 0 real solutions. Right? And so on. If we have a third degree, it could have 3, 2, 1 solutions. So the zeros of a function, we've got many names for those. Okay, we can call the zeros roots. We can call them solutions. We can call them x-intercepts. Okay, and that's kind of what these first 3 bullets down here say. So if f of c equals 0, okay, that's saying that some point c0 is on the graph, right? So if the y-coordinate is 0, that means it's an x-intercept, or a root, or a solution. So if that point's on the graph, then c is a 0, c is a solution, a root, c is an x-intercept of the graph, right? C0 is on the graph. But this last point, okay, is a little bit different, okay, but this is a very important idea. If C0, okay, is on the graph, or C is a solution, then the factor x minus c is a part of the polynomial. For example, if I know that I've got a quadratic with zeros of -2 and 4, well, then I know that the factor x minus -2, which would be the same as x plus 2, is part of my polynomial, as is x minus 4. All right? And we'll look at that a lot more here in just a second. So the next part is a little bit of vocab. All right? So the number of times a 0 appears in a polynomial is called its multiplicity. Okay? We could have the same 0 show up multiple times. Multiplicity. Okay, so however many times it shows up is its multiplicity. For example, okay, if part of my polynomial is x plus 3, well, let me just write out a whole polynomial here. So f of x equals x plus 3 squared times x minus 1 times x plus 7 to the 5th power. Okay, so this 0, okay, which would be -3, shows up twice. Okay, it's got a multiplicity of 2. This 0, which would be +1, has a multiplicity of 1. And this 0, which would be -7, has a multiplicity of 5. Okay, it shows up 5 times. If you add up all the multiplicities of all zeros, okay, now this all zeros includes both real and imaginary. Okay, in this section, we're just going to look at reals. Okay, it will be the same as the degree of the function. If you add up all the multiplicities of all the zeros, including both real and imaginary, okay, but for our purposes for this section, we're just going to look at reals. Okay, it'll be the same as the degree. Now, this one is key when we look at a graph of a function. Okay, a 0 with an odd multiplicity will cross the x-axis, but a 0 with an even multiplicity will just touch the x-axis. Okay, so for example, up here, this x plus 3, so my 0 of -3, has an even multiplicity. Okay, it's got a multiplicity of 2. That means when I'm graphing this, the graph will just touch the x-axis at -3 and then turn around. Okay, it will not cross. However, here, my 0 of -7 will cross the x-axis because it has a multiplicity of 5, which is odd. Okay, and we'll look at examples of graphing that in just a second. Now, another interesting point is that if we have a polynomial of degree n, then the graph of f has at most n minus 1 turning points. Okay, we talked about what a turning point was in the last chapter, right? But short, simple example could be a graph that looks like this. Okay, this hopefully we can recognize would be a cubic function. Okay, this shape looks like a third-degree function, and it has 2 turning points, right? We also called those local mins or local maxes, or relative mins or relative maxes. So if this is a third-degree polynomial, this one has 2 turning points. Now it is possible to have fewer than 2, but the most that it could have is 1 fewer than the degree. So a 4th-degree polynomial has at most 3 turning points. A 5th-degree polynomial has at most 4 turning points, and so on. All right, so let's take a look at some examples here. All right, so first, we want to find the real zeros, state the multiplicity of each, and then state whether the graph of f crosses or touches the x-axis at each zero. So this first zero, okay, x minus 1, well, I guess I can write this out first. What we're actually doing here, we're saying we're solving this equation, right? We're setting this factor equal to 0. Then I would add 1 over and get x equals 1. Okay, so basically what we end up doing is just taking the opposite sign whenever we have a factor like this. So x equals 1 is a 0. It only shows up once, right? The degree is 1. So this has a multiplicity of 1. So since the multiplicity is odd, that means this will cross the x-axis. The second one would be x equals negative 2. Again, this only has a multiplicity of 1, which means it will cross the x-axis. And the third one, that would be x equals 3. Again, just a multiplicity of 1, which means it will cross the x-axis at this point. All right. So the next one, okay, let's do one more together, and then I'll have you guys try a couple. So my first 0 would be x equals negative 1. It has a multiplicity of 1, and that means that the graph crosses the x-axis at this point. The second 0 would be x equals negative 5. This multiplicity is 5, or I'm sorry, it's not 5, is 2, right? My exponent is 2. Since that multiplicity is even, that means that this will just touch the x-axis. All right, so you guys try this one, okay? State each 0, state its multiplicity, and then whether that means it will touch or cross the x-axis. All right, so the first one would be x equals 3. Its multiplicity would be 3, and that means it crosses the x-axis. The second one would be x equals negative 1. Its multiplicity would be 1. It only shows up once. And since that's odd, that will also cross the x-axis. All right? You guys go ahead and try this one as well then. All right, the first one, okay, we have to look at this factor. Well, this factor, if I set negative x squared equal to 0 and solve, I would just get x equals 0, right? Its multiplicity is 2, which means it just touches the x-axis. Okay, and we'll take a look at what that means visually here in a second, whether it crosses or touches. My second one would be x equals 9. Its multiplicity is 1, and that means it crosses the x-axis. And my third one, x equals negative 1. that has a multiplicity of 2, and that means it just touches the x-axis. Okay? So let's go the other way now. Okay, let's say, given a graph, I want to try to write a function. Okay, so now it tells me that we're just going to leave the leading coefficient as 1 or -1. So there's a couple of things that I need to look at here. The first is I want to look at where the graph crosses or touches the x-axis, okay, my zeros. So I see a 0 here at -1. That graph crosses the x-axis at -1. Okay, so I know that x equals -1 is a 0, and its multiplicity is odd. Okay, and it says smallest degree. So if we say smallest degree, that means if it crosses, we're going to assume the multiplicity is 1. If it touches, we're just going to assume the multiplicity is 2. Okay, so my other 0 is at x equals +3, and that has a multiplicity of 2. So what this means, okay, how I can turn this into an equation, right? A solution of x equals -1 means the factor x plus 1 will be part of my polynomial, right? Or x minus -1. We said it has a multiplicity of 1, so I'll just leave my exponent as a 1. This tells me that x minus 3 will be a factor. But since the graph just touches the x-axis, I know that has to have an even multiplicity. So since we're the smallest even number that we'll look at is 2. So this would be how I would write a function. Okay? The other thing we have to take into account is whether my leading coefficient should be +1 or -1. And for that, we have to think about end behaviors that we talked about during class today. So the end behaviors here, as x goes to -infinity, f of x goes to -infinity, and as x goes to +infinity, f of x goes to +infinity. Those are the end behaviors of a positive odd function. Okay, so my coefficient we're going to leave as +1 for this one. All right. So let's do one more together here. Okay, and on your paper it says take a look at number 56 out of the book. So here's a picture of that. So I want to look to see where my zeros are. So I've got a 0 at -1, at +1, and at +3. Each of those touch the x-axis. Each of those cross the x-axis. So we're going to assume that each of those multiplicities is just 1, right? So we've got x equals -1, x equals +1, and x equals +3, right? And each multiplicity is just 1, right? Mult of 1 for each one of these. So I can write my function as f of x equals x plus 1 times x minus 1 times x minus 3. Okay, so then the other thing we need to look at is the end behaviors. Okay, here as x goes to -infinity, f of x is going to +infinity, and as x goes to +infinity, f of x goes to -infinity. Those are the characteristics of a negative odd graph, or a negative odd degree. So in this case, I need to throw a negative sign out front. Okay, so we need to first look at the zeros, check their multiplicities, and then see whether I should have a positive or a negative out front. And we get that from the end behaviors. Okay, so why don't you guys take a look at the next two here. Okay, so here is the graph of 58. All right, so write a possible function for this graph. All right, so if I look at my zeros, I'm at -1, and I'm just touching at -1. So that we will say has a multiplicity, or an even multiplicity. So we're going for the smallest even number. then x equals 2, and that crosses, so that will have a multiplicity of 1. So to write my function, I can say x plus 1, and that'll be squared, because we're saying it has a multiplicity of 2, times x minus 2. Then we have to check our end behaviors. So as x goes to negative infinity, y goes to positive infinity, and as x goes to positive infinity, y goes to negative infinity. Those are the characteristics of a negative odd degree. So we need a negative sign out front. All right? So you guys also go ahead and try number 60 out of the book here. All right, so I've got zeros at negative 2 and positive 2. Both of those just touch the graph. Right? So x equals negative 2, that means we would have an even multiplicity, and x equals positive 2 with an even multiplicity. So to write my function, I can say x plus 2 squared times x minus 2 squared. Now again, we have to check the end behaviors. Okay? As x goes to negative infinity, f of x is going to negative infinity, and as x goes to positive infinity, f of x is going to negative infinity. Those are the characteristics of a negative even degree. All right? So just to have one more big example here. So given this function, I want to graph it using all of these things that we've talked about. So what we're going to do is find the zeros by factoring this, and then think about end behaviors to sketch a rough graph here. So to factor this, first we want to take out a GCF, so I can take an x squared out. So x squared, and I'd be left with x squared minus 2x minus 8. So now I can x factor this. So I want two numbers that multiply to negative 8 that add to negative 2. So I think negative 4 and positive 2 would work. So this would become x minus 4 and x plus 2. Okay, so from this now, I can see that x equals 0 will be a solution, and that will have a multiplicity of 2. X equals 4 will be a solution, and that will have a multiplicity of 1. And x equals negative 2 will be a solution, and that will have a multiplicity of 1 as well. So I can put those on my graph here. I know the graph of a 0 at negative 2, a 0 at 0, and a 0 at 4. Okay, well now, okay, let's think about the end behaviors. Okay, so this is a positive fourth degree, right? Positive fourth degree means my end behaviors will both be going up. Okay, positive even means end behaviors go up on both sides. So if we want to sketch a rough graph here, okay, so at negative 2 we're going to cross. So I don't exactly know where I am over here, but I know I'm going to be going up. So I'm going to cross here. Then this has an even multiplicity, right? X equals 0 has an even multiplicity. So I'm just going to come up and touch right here, and then bounce back down, and then somewhere, I mean, this is a rough sketch, right? I don't really know how far down to go. We could plug in points, but we're not going to worry about that right now. Okay, what we're worried about is finding the zeros, finding the multiplicities of the zeros, so we know whether to cross or just touch, and then the end behaviors. Okay, so and then we cross here at 4, and then this will just keep going up forever. Okay, so this graph, again, a rough sketch would look something like this. What we care about are the zeros are in the right place, we cross and touch at the right places, and then our end behaviors are correct. That's what I'm looking for on your rough sketches here. All right. The final idea on these notes is the intermediate value theorem. Okay, this idea is useful for locating a region where we could find a 0. All right, so the idea here is just saying if I have, let me sketch out what this is saying. If I have two x values, right, say we've got at A and we've got a value at B. If the y values have opposite signs, right, so if my f of A is down here, and then my f of B is up here, right, they have opposite signs, meaning one's positive and one's negative, then that means somewhere in between A and B, as long as this is a continuous function, somewhere, I don't know exactly where, right? This function could do a bunch of crazy things, but somewhere in between there, it'll have to cross the x-axis, okay? So for this example here, okay, it says show that this function has a 0 in between x equals 1 and x equals 2. Well, let's just plug those in and see what we get. So if I plug 1 in here, negative 2 times 1 cubed plus 4 times 1 plus 5. We get, let's see, negative 2 plus 4 is 2 plus 5 is 7. And if I plug in 2, negative 2 times 2 cubed plus 4 times 2 plus 5, what do we get? 8 times negative 2 is negative 16, plus 8 is negative 8, plus 5 is negative 3. So since I got y values with opposite signs, okay, and this is a polynomial, meaning it's continuous, that somewhere in between these 2 points, we have to cross the x-axis. Okay, we don't know exactly where, but somewhere in between 1 and 2, I have to cross the x-axis. Okay, so this work here proves that somewhere in between 1 and 2, there's a 0. All right, so tomorrow in class, we will take a look at the homework. I mean, you're welcome to start it now. I will post it on Schoology, okay, but